I'm Dara O Briain. Welcome to my school of hard sums. We're here to examine one big question, which is, as you encounter all the practical problems of everyday life, what's the best approach to take? Do you go about things methodically, in a rational way, or just steam in regardless and hope for the best? This show is a battle of brain versus brawn, and tonight I shall be playing the role of brain. Each week, my grey matter is pitched against the brute force of my two comic guests, as we tackle three increasingly fiendish problems that we've never seen before. Oxford professor Marcus du Sautoy is here to set the questions and decide whose approach is the best. And to keep us all on our toes, there's a bunch of brainy maths students having a crack as well. But first, let's meet my competition for tonight. Susan Calman and Richard Herring. Hello, you two.
Hello.
Very, very good. Are you puzzle people? Do you problem
Yeah,
people?
I kind of do up to a point. I'm not very good at anything in 3 dimensions, though. I kind of like things in 2 dimensions. But, you know...
life, though, isn't that?
Three-dimensional? I suppose it is. But, you know, when you have to kind of make a cube out of a flat thing or something like that, anything like that, or say which is the object made
Spatial relations.
I can't do those things.
OK, you...
I'm much more of a kind of a bulldozer type approach to problems, in that I get very annoyed if I can't do that. So Richard's quite safe and I'm quite gung-ho, so it's kind of like the A-team type situation. Just blow it up and we'll see what happens.
Are either of you in the A-team? Which one
It'd be quite a good A-team. I'm a throw it at the wall and see if it sticks kind of gal.
OK, that is exactly what we need for this.
Yes.
What kind of teams do we have? Do we have a team for this?
Yeah, we have. It's how maths can feel the force. So we've got an opening problem just to get your neurons firing. So you've got probably going to be working together on this one, actually, because you're all 3 members of the British Plank Appreciation Society. So I've got some planks over here. Do you want to pick up your...
So we're the British Plank Association. I was more wondering how we would have met up, whether it was through a magazine.
Oh, the internet.
The internet. Right,
internet. Google automatically routes people together who type planks.
Okay.
If you type in planking, actually, you get some quite interesting things.
Well, planking is a thing.
Yes.
It is.
So we're 3 single gals.
Going planking. Come planking with me over here, then. So here are your planks.
Standard 2x4, isn't it? Yeah.
It's good that we're in height on.
I just realised that, It's like the ascent, the ascent of man. This stage, OK.
Progress, yes. So you're each going to take a plank and you've got to create a structure which can support something in the middle of the circle that you've made. Or triangle, actually, because there are 3 of you. So if you'd like to take your planks around here, and
I'll take
we can get you going.
Right, so there's 3 planks of equal length, and we need to arrange them in such a way that if we each hold one at one end, they could somehow support someone in the middle.
I like the way that you're holding your plank, though. I'm going to do that as well. I enjoy that.
Fallen into a broom situation, which is the...
So it might be better, actually, if you're going to be able to hold it at one end.
Like that?
Oh, hang on.
Exactly, there we go. Yeah. So in other words,
if we lay them like this, hang on, do you want to...
Lay them on top of each other like that.
Yes, that's correct.
I'm already feeling that quite heavy.
That's just
you think you could
planks.
Do you think you could support a student on top of it?
No.
No, it's impossible. You need to make a bridge of some kind.
So I'm now supporting it like that.
So I would support it like that.
Yes.
And would you come in there?
How's that?
No, you're also supposed to hold it.
The student's going to be there, so at the moment that's a bit rubbish.
OK, but they could spread themselves. We're doing a lot of the work here.
So if you have it as a kind of a... OK, if you're...
OK.
Do out that way. Go out that way, right? Out that way,
right? OK, hold on a second.
Yeah. OK, no.
Right, OK.
Hold that, right, OK.
OK.
Right. And this as well.
OK.
No, seriously.
Yeah, OK.
Yeah.
Right,
all the way to the end.
All the way to the end.
All the way to the end.
Right.
So just I'll help you.
Oh, thank you.
Right, so both...
And then actually...
Right, and then you hold it.
Hold it.
Go to the end there.
Right.
OK, now.
OK.
And then put the C on top of this.
Could I put in a little mathematical term here?
Yeah.
OK.
Symmetry.
Yes.
Whatever anyone is doing, the other one will be doing essentially the same thing.
Triangle.
Symmetry.
Are you just naming... Sorry, Susan, let that
Equilateral triangle.
No problem.
Lay in the ground so we're not tiring ourselves. Put it on the ground.
OK.
But they've got... One of them's got to... One or 2 of them have got to support the other one, right?
Exactly.
If they're all, like, interlocked, will that somehow... One of them, that would surely mean... If that one's underneath that one...
Now, this is...
It's nice, that, but I'm not sure what that actually...
But then it doesn't... If they're in the middle, that won't work.
But how could you get those planks nearer the middle?
You
just push them
Go on, then.
Yeah.
OK. So if we push them in a little bit...
Sorry, lift it up.
Sorry, I'll lift it. Like that.
And then you do that. OK, grand.
OK, and this one, is it this one going that way or that way?
Exactly,
this one's going that way, actually.
That way?
Yeah, exactly.
So push that one to about there. Is that about right?
This one, yeah.
OK, fine.
OK.
Shall we?
Shall we? Try and...
All right, remember to bend your knees.
OK.
Excellent.
Okay.
Do you think you can support one of our students?
Yes, I do think we can, yeah.
OK, any volunteers? OK, let's
My
have
goodness.
Samantha.
Right, we're putting on a plank, or we've held safety issues.
All right.
Okay.
So you go down
Right,
a little bit.
go down a little bit.
Knees, remember.
OK, Samantha.
Thank you.
Good luck. Thanks.
And up she goes.
Oh, yeah, actually.
Yeah? That's very good.
Let's examine the forces at play in our arrangement of planks. My plank had to push a force upwards to support Susan's plank, and hers pushed an equal force back down on mine. So we used Richard's plank to support mine, but then Susan's plank had to support Richard's. The force downwards due to gravity is passed anti-clockwise around the groove, and the upwards supportive force is passed back clockwise, balancing the structure. Scientifically, we say that all the forces in the system are in equilibrium. It can take any weight in the centre, so long as our legs are strong enough to support the outside.
One of the people that used this kind of idea in architecture was Christopher Wren. One of the first buildings he built as a young architect is the Sheldonian Theatre, which is where we give out degrees in Oxford. But inside, they didn't want any columns supporting the roof because they used to do dancing inside here. And he used this idea, not with triangles, but with squares. So he created squares with the planks, had them weaving over and under, all the way to the sides. In fact, he ended up having to solve a system of 25 simultaneous linear equations in order to work out how to do this. So, a piece of maths in action.
Wow. Well, they wouldn't get insurance for a building like that these days, though. I suspect they would probably want some form of support structure in place. If I said I was going to build a house with
An interlocking wood thing, but you solve the equations required.
Well, I don't know.
Yeah.
You've got some mathematics to support you. That's, that
And
doesn't...
tell you, the banks love that.
Well, one plank goes.
The whole lot comes
Really
in.
goes and tumbling into
I guess it, yeah.
Yeah, excellent. Do we solve that? Is there
Yeah, I think that's it. Yeah. I think you get your bronze badge for the British Plank Appreciation Society.
Can't wait for our caravanning holiday together. It's going to be a blast.
But I've got to make a decision, I think, between Brain and Brawn, and actually, I think probably Brawn did it because Richard, you really came up with that idea of the interweaving. So Brawn,
me and Christopher Wren.
Christopher, yes,
It was a joint thing.
and Richard have the first round.
Fantastic. Well done, Richard. Braun wins that one.
Yeah.
Very good. But it was very much a brawny type.
It was a very much a Brawn.
Yeah. So, what's the next question?
The next question is all about weighing. So you're going to be playing grossers in this round. You're going on holiday and you have a set of weights, 1 to 40. You want to take as few weights as possible such you can still measure all the weights all the way up to 40. So what's the minimum number of weights you'll need to take?
You have a set of individual weights, 1 to 40 ounces, and some balance scales. You need to be able to measure the weight of any other object between 1 and 40 ounces. For some reason, you're taking your scales on holiday, so you want to take as few weights as possible. What is the minimum number of weights you should pack to still be able to measure 1 to 40 ounces?
Right.
Does the fruit have anything?
The fruit will be the test of whether you can actually weigh some of these items.
With as few as possible.
Yeah.
I like the way
So
there's
prove
five portions of fruit. It's like a hidden message.
Yeah.
It is.
Hey kids,
Maybe.
this is as many as you have to get to on any given day to not die.
All those bananas.
I agree. That's just one portion. of
That's
fruit.
just one portion.
5 bananas.
It's just one.
I reckon we'll definitely need the 1 ounce bag.
That's
my
always a good start. I
contribution.
think it's a good start.
We'll
yeah.
definitely need to take that.
Why do you need the 1 ounce?
Because you'll always, there must be points where you'll get a single unit over whatever else we're putting together. They're prime numbers, I guess, I'm going for.
Oh,
So maybe.
I like your...
Can I throw in a question? By the way?
Yes.
Can we add and subtract weights?
In what sense?
In the sense that if you have a 2 here and a 3 here, it's the same as having a 1 here and nothing
Exactly, so you might not need
Herring's argument might be blown out of the water straight away.
I'm taking the 1 out.
I'm
Take it in my hand luggage. I don't care about the rest of you. We can make 40 up out of all sorts of
We can
numbers.
make 40 up out of anything. Now, Dara's at the board now, so let's do it like it's money.
Yeah. 1p, 2p, 5p, 10p.
Yeah.
20p. Let's see if we can do it with this and then see if we can cut it down. And, then there's
Well, see, then...
there isn't a 50, so...
There's not a 50.
This is quite a good way to do it non-mathematically.
Yes.
So we'll just say, so we've got, that's 40.
Oh, OK. Do you want to try that out? We could try...
Right.
Bananas are 34,
OK.
so you could test your
Here,
theory
you do
out.
that, and I'll do the bananas.
Yeah. So is this one where you have to put all in one side, or...?
Yes, you have to put them all in one
We're
side.
just working on the all-on-one-side theory,
okay,
and then we might be able to cut it down later.
We might be able to, but just initially we're going...
Is it just the banana?
So you've got a 20, a 10, and how
No,
have you
that
got
just
the 4?
doesn't... Oh,
Maybe
it's
the
caught.
plate as
It's
well.
caught.
Oh, there we go.
Oh, yeah, there you go. How do you get the 4?
We've got 3 and a 1.
3 and a 1.
3 and a
Okay,
1.
there you go.
So that works
Yeah,
with the
that's good.
bananas.
We've got, I think with those, we've got it all
6.
covered even without doing the double thing. So we might be able to do some. We might be able to get rid of some of them by.
Yeah.
So we've got it down to
so how
definitely
many
1,
you
2,
got?
3, 4, 5. We've got 6.
6, OK.
Right, we're going to take a little bit more time to go to this one, because it's a very complex problem, obviously. We'll give a solution after the break, but more interestingly, after the break, we'll have our big problem for the week, and we'll find out exactly why Richard and Susan have been out and about doing this.
Gosh, this is the most impressive seduction technique I've ever experienced.
Thank you.
Because bear in mind, Elton will be livid.
I think Dara's going to beat us.
Welcome back to School of Hard Sums, the programme in which we pit using maths against just using good instinct in solving problems. The problem is set for us as ever by our problem setter, Professor Marcus du Sautoy. We have Richard Herring, Susan Calman here, and we have our students here, who I think have really raced on in this one and are looking pretty comfortable, to be honest.
Have we got some ideas how they would do it?
No, I think they all pool their brains together like some sort of Borg thing from Star Trek, and then...
Smug's the word I would use.
Yes, that is yeah. So we're trying to work out the smallest number of weights we can use to measure the weight of any object between 1 and 40 ounces using a traditional set of scales. For some reason, we're taking our scales on holiday, so we need to keep the selection of weights as small as possible.
Dara, how are you getting on over there?
There's a very straightforward way you can get just do it with 1, 2, 3, 4, 5. With 6.
Yeah, we've got
but
6.
we're working our way down again.
How did you get it with 6?
Well, you get it with 6 by just taking its powers of 2, right?
Yeah.
If I got 1 and 2, then I can get 3. And then so I can add them to get 3. Then I stick in 4.
Yeah.
And I can therefore get 4 plus 1, 4 plus 2, and 4 plus 1 plus 2. I'll give you 7. So I stick in another 1. And that's the way of doing it if all you can do is add them.
Yeah.
But if you can subtract them as well, then it's actually more interesting, because then you can 1, and then you don't need 2, because if you got 3, then you can have 3 minus 1 to get 2.
You get rid of 2.
And then you can it kind of works out.
Well, in fact, the powers of 2, of course, is how computers count.
Of course.
Because you're doing it in binaries. So,
Yes.
yeah.
So could we get rid of 2?
I think we could
efficient,
get rid of 2 and still do everything.
Oh, wow.
Let's see by that logic. So let's see if we can.
I'm struggling to see how we can do it in less than 6.
Yeah, OK, that might be...
For practical.
Yeah, you could settle with that.
But I think
can I go over there for a second, just to clear my throat?
some help from the students.
You can.
I'm just going to clear my throat.
By all means.
For a second.
Clear your throat down that end. It's ridiculous. You're going to live a horse. It's kind of so too loud.
But I think...
That's an equation. You've done an equation, Richard.
That's cheating.
That's an actual
We're not allowed
equation.
to do that.
Yeah.
What does that mean?
Oh, that's just an interval.
Oh, that's just an interval, Richard. It's just an interval.
OK.
They're just writing equations.
No.
It doesn't even make any sense.
Is it that...
Who's to say that we're not going to accomplish something that all of those people can't if we're just given a bit of space?
I think we can say. I think we can say.
Pressure on us all the time to, you know...
Are you going to commit to this then?
No,
there's no...
this was just an experiment.
Time is ticking on, though, so...
Right,
Well, we're at the moment, we're on that. We're on 5.
5 is, at the moment, the one that we're certain of. OK.
What would you need, therefore, to get 2?
Another 1.
That's a good idea, but yeah, that just means you're carrying 2 1s. That's the thing. What other number can you get 2 from?
This is the look I used to give my
3.
father
We'll
when he was trying to explain
3 and 1
me.
makes 2.
You're right. You're
So,
absolutely
but we haven't
right.
got we had a 3 before, but now we haven't got a 3. So if we get rid of the 2 to the 3,
That's
that
a
actually
5.
says 5.
That's
sorry.
a 5.
5 for a second. OK, grand.
Have we lost that?
So now you got a 1 and a 3.
Yeah, we've got 1 and a 3.
What can you make with that?
4.
4. So
Yeah.
we don't need the 4.
There we go. Right.
Feel it.
It's
Can
great.
you feel
It's a good
it?
feeling. I know.
That's
Yeah.
math.
We were working
This is
from our way
You've
up.
already gone from 3 things now to just 2.
Yeah.
Already
And
you're moving further on. You're just not quite maximising.
And 11.
You're not quite maximising with that.
So these 2 can be replaced by 1, I think, is what we're saying. So we could get something like 12 or 11 or 13.
How many of you saw the pattern and went for it?
7.
Did you all just go, there's a 1, a 3 and a 9, I bet the next one is 27?
Yep. And then we realised that it was past 3.
Yeah. I mean, is there a simply like a clever expression rather than... Because
I'm going to call time on this, so yeah, you've got to commit.
We'll have to commit to 5.
So, Dara, do you think you can beat 5?
I think I'm being fine, because I think it'll be done in 4, but you're really, really close.
Okay.
Yes.
Yeah, OK.
Yeah, and I also think if you ask them, they will all say 4 as well.
So, students, how many can you do it in? 4. OK, Dara, how can you do it in 4? What are you
do
going
it
to
in
choose?
4. You see that it works with 1, 3 and 9, and anyone who's vaguely mathematically goes, well, they're just powers of 3. So I bet I know what the next one is, 27. Right? Yeah, 27, right? Yeah, so that's really what I bet half the people here saw 1, 3, 9 and went, bing, must be 27, right?
The key to solving this problem was realising you could build different value weights by adding them together on the same side of the scales and by subtracting one from the other by putting weights on both sides of the scales. If you could only add weights, then you would need to take the 1 ounce weight, the 2 ounce, you'd use those to make 3 ounces, then you'd need the 4, 1 plus 2 plus 4 gets you as far as 7, so then you need the 8 ounce weight, and so on. The next weight you need is always twice the previous one. This is working in powers of 2, i.e. 1 by 2 makes 2, 1 by 2 by 2 makes 4, 1 by 2 by 2 by 2 makes 8, and so on. But because we can add weights upwards from one number and subtract weights downwards from the next, in our sequence, the next number can be 3 times the previous. So we're saying we're working in powers of 3, and that's what gave us the sequence 1, 3, 9, 27.
But you got 1, 3, 8,
Yeah.
28.
Yeah.
You're really, really irritatingly, just achingly close.
In our defence, people kept saying the word binary.
There's a lot of
So in
binary
our
going on.
defence, I think,
But,
you know...
but I presume this is I'll ask you this one, because in binary it's either on or off, right? But in this ternary, these things can be either plus nothing at all or minus.
Yes,
so it's
exactly.
got 3 states.
There's 3 states, that's right. It's not there, or you're taking it away, or you're adding it. So the taking away goes on one side of the balance, it not being there at all, or adding it goes on the other side.
OK, grand. And the 3 states are in some way connected to the fact that it's going to be 3s that you have as
Exactly,
powers.
that's right. So it's powers of 3 are the key to this. So, but I think Dara, you won out, and the students as well. So Brian has got the second round. So it's even Stevens here.
OK, we've still got a big problem to do, and you've already done this one. We've still got more to do here. We want you to join us after the break when we tackle the big problem this week.
But before that, here's something to ponder over the break. Using 2 straight lines, can you divide this clock face into 3 sections so that the totals of the numbers in each section are the same? But before the break, I asked, can you divide this clock face into 3 sections using 2 straight lines so that the totals of the numbers in each section are the same? The answer is yes, you can. Draw the lines here and here so that each section totals 26.
So welcome back to School of Hard Sums, our show in which we pit brawn against brains. In this case, the brawn is being played by Richard Herring and Susan Calman in the battle to find out what the best approach is for solving problems. We have a big problem, Marcus, to do we?
Yes, we have. You're going to be playing a florist in this round. And,
OK.
You've landed an incredible job, actually, because Elton John's commissioned you to make a flower chandelier.
Wow, if you get the Elton John commission, it is florist heaven.
Exactly.
It's an easy street for florists, yeah.
So you've got these 5 baskets, and they are made up of different flowers and different weights. So the smallest one is anthurium flowers, which are 1.5 kilograms. You've got jaberas, which weigh 3 kilograms, ranunculi at 4.5 kilograms, tulips 6 kilograms, and the largest is a load of roses, which weighs 7.5 kilograms. So the chandelier is circular in shape, and it's got 12 hooks.
Yep.
And he wants this thing to balance perfectly from a chain in the middle.
And Elton likes his flowers clumped in a kind of a, just no overspill, no artistic...
He likes these 5 clumped ones, but what he's really particular about is that this thing should be absolutely level, horizontal. You've got to find some way to
Fine.
To get them to balance.
OK. That's great. I'm really looking forward to doing this one. I have to do this in a kind of a scribbly way, but you actually went out and tried this.
We did.
We were very, very conscious that while we were doing the problem that it was Elton John.
Yeah.
And so we really tried to artistically express ourselves whilst arranging the flowers, which is something that the maths students over there with their scribbly, they didn't have to have the vision.
They can't understand that. They can't understand that.
OK, let's see how Richard and Susan got up.
As you know, Susan, I've been trying to seduce you for many years, unsuccessfully for some reason, but I know that chicks love flowers, so I've brought you here to a florist.
Great.
I couldn't afford all of those, so I've got you this one. That's for you.
Oh, it's beautiful.
Yeah.
It really is. Gosh, this is the most impressive seduction technique I've ever experienced.
Thank you.
Usually I just get a bag of chips. So, this is the flower table. So these are our flowers that we have to work with.
Props, we've got Elton John's gigantic golden ring. That's the circle of life.
Right.
There's the 5 baskets with moss, loads of scissors.
Secateurs, darling. Secateurs, we're gardeners now.
I think we should put the flowers in these baskets.
That's very good.
The weights that were prescribed.
Okay. What's the first one that we're doing?
The anthurium.
The anthurium basket must be 1.5 kilograms. Maybe a good thing to do would be to arrange them. Oh, wow. Now, do you know, if I'd wanted that, I would have asked for it.
Right, that is, we've still got, like, 100 grams.
Get some greenery.
That's it, exactly. That's it, we've got it.
Gerbera, 3 kilograms.
I'll be in charge of taking off the polythene.
How much does it mean to be? It's OK. It's OK.
I think we might need to take this a bit more seriously.
I'm taking it very seriously.
That's going to lose a lot of weight. Hey, why don't we put just that bit? Still 0.6 of a kilo off. Could put a torch in it.
Stick a torch in it. Right?
Yeah.
So that's that done. So next one.
4.5 kilograms of ranunculus.
This is what it's about. It's about the beauty of the flower.
Your mum's going to be proud.
She'll be upset I'm not wearing a dress again, though.
Oh,
That's the thing. I'll be flower arranging, but do you know what she'll be thinking?
She'll be thinking, isn't Richard Herring an attractive young man? Maybe. Maybe the two of us could get together.
Oh,
Think of the children we'd have.
Oh, No!
Baby.
It's got really flirtatious there, hasn't it? Oh, Richard, you're so handsome.
Yep, that's how I flower arrange.
Okay, how much is it? 6?
6 kilograms. Let's see how we're doing.
Where are we at?
5.4 kilograms.
There are no more tulips. Oh, they smell horrible! It smells like a dog.
OK, last one.
7.5.
I'm going to need some padding here.
See that chain? Put that in the bottom. Add the torch.
Oh, God, torches don't weigh as much as you think. Bottle of water.
Oh, you've got a bottle of water.
I think that'll do it.
7.5 kilograms. Richard, come here for a second.
Yes.
Come here for a second. Before we say we have completed this part of the task, can I just confirm that these arrangements weigh enough and are fabulous? Because bear in mind, Elton will be livid.
This is how I want it
This
to
is
be.
the definition of fabulous.
Yeah. That one looks nice.
So when did this show turn into a romantic comedy?
It was like Sandra Bullock.
We're an unlikely couple. We've come together through our love of flowers.
Is the second video you running through the rain?
Yes.
We're just doing each other in the second one.
Yes. Rather
We're hanging off the chandelier.
Yeah.
Who knew maths could be so romantic?
Yeah. I always can't believe that this show has a really high flower budget. Because, you know,
do you know how much Elton John spent on flowers?
Yeah, but I also know how
months?
much the budget of Derby School of Our Sons is. OK, I'll go off and do this. OK. Dearie me.
So you must arrange flowers around this ornate chandelier for a lavish party at Elton John's house. He's pretty specific with his floral arrangements, and he wants his baskets of flowers to weigh 1.5 kilograms, 3, 4.5, 6, and finally the heaviest at 7.5 kilograms. There's 12 hooks in the chandelier, and you need to position the flowers so that it hangs level, or Elton will be livid.
Now, the theme of this was how maths can feel the force. So we've got a lot of forces balancing and things like this. I've got this rather curious contraption here. So I wonder what you think will happen if I start to push this contraption over the edge of the table.
Can I just...
Yeah.
Yeah,
it is just cloth. There's no sort of...
He's not a magician, he's a mathematician.
Just checking.
There's not a trick
in case, you know, there was some form of...
It is maths, not magic, you know.
Yeah.
So that's just cloth supporting there, so actually it should just flop down.
Yeah.
This thing continues to balance, although that is just... there's no hinge there, it's just cloth.
Oh.
If we keep on going, and rather amazingly, the whole thing actually balances. So you're just holding it here, yet everything on this side is just cloth there. It should be flopping down.
It's not flopping down.
It's not flopping down because...
Sorry, Richard.
Oh, yeah, it rather likes you, Richard.
Yes.
It's like a puppet from a kind of Czech theatre.
But actually, this is a mathematical equation in action, in some sense, because the reason this little bit balances here, of course, is because of the weights that are on this side. So balance is all about this equation. The weight times the distance from the pivot has got to balance either side.
Mm-hmm. And does that have any practical purpose in life? Would you see that anywhere?
Absolutely.
Where would you see? It wasn't a sarcastic question.
No, but
it wasn't a sarcastic question. It was where would I find this?
Where might you find something like this?
In a bridge? That's a lie, Susan.
No,
That's a lie.
actually, it's not a bad answer.
Oh.
Yeah. There's one architect who loved using mathematics like this, Gaudi.
Yeah.
So there's a famous building in Barcelona.
Vida Familia.
Yes, exactly. Yeah. He used a lot of mathematics, actually, to create extraordinary shapes inside here, which almost looked like they couldn't stand up. So, in fact, there's a beautiful construction under that Gaudi used, which you can find underneath the Sagrada de Familia, which is a lot of chains hanging with weights on it. And he knows that if he turns this structure upside down, he can create that shape inside the building. So we actually have a chance to look at some of Dara's workings. So you've got a tablet at your side. It should show some of what he's been drawing on the board.
Yeah.
So he's marked out the 12 positions and worked out the geometry of where they are, these lines. So you can see these triangles, which you've got inside here, are very classic triangles. They're 30, 60, 90 triangles, which you can use a bit of Pythagoras to work out what the length is on these. Here we've got root 3/2 comes from Pythagoras' theorem.
What's that there?
The X. Yeah, so he's put it on a sort of graph paper, basically.
Oh, so it's an X and Y axis.
So the weight times the distance from the centre has got to be the same on both sides of the vertical and horizontal line. You remember on a seesaw, if you're the wrong weights, you can actually even it up by the heavier one going slightly closer to the centre. So basically Dara's saying, OK, this is a seesaw, and I've got to balance things either side of the x-axis, so he needs to know the distances away from the x-axis. That's why he's done all of this Pythagoras' theorem.
Can I step in for 1 second and go, have you deliberately drawn the Death Star?
Yeah.
As long as you fire the missile into there, yeah, you're fine.
Well, I'm finished.
You're finished? Yeah. In a nice, elegant way?
Oh, my arse, no. It was a proper physicist way. However, I want to see how you two did. I want to see episode 2 of the burgeoning romance between Susan and Richard. Let's have a look how they solve the problem.
OK, Susan. This is what we have to do.
Yeah.
We have 5 baskets. They go at 1.5 kilogram increments. That might be important.
I hadn't spotted that.
We've got a wheel. It's got 12 hooks numbered 1 to 12. That's number 12 there. 12. We have to hang this so it levels out.
Levels.
Let's put the little one on number 1.
Number 1.
Do you have any idea where things should go? Should we just take
I have, at this point in time, no idea about anything. Oh,
yeah, so you're...
OK.
This is the one with the torch in. Number 11.
Oh.
So we want to kind of go...
OK, yes.
Let's try the massive, massive one. Whoa!
Right, OK, so... Oh, you're so strong and good.
Thank you.
Right, I'm leveling out.
So we need something the size of Susan Calman.
Perhaps Susan Calman.
And that will work. Let's try that one there.
OK. Oh,
Can't get my thing into my thing.
Okay.
There you go, perfect, we've done it. That should be in there. It's pretty close.
It's pretty close.
I mean, that's nearly there, isn't it?
That's nearly there.
It is slightly going that way, so I wonder if we can do better. These two and that way the same.
Yeah.
If that was there and those two were over there...
Let's try it.
It's less good.
It's less good.
How about this one?
Okay.
Goes to there.
OK.
Well,
no,
I don't think so.
That's not right, Richard.
No.
No. How about the wee one on the same one as that? No. Stupid.
No.
Stupid hand.
Is there something in putting them close together?
No.
This could take a few years.
Try it there. Richard.
No.
Oh!
Oh. I think Dara's going to beat us. I think we can get it nearly even and then just work out where to put the little one.
OK. OK.
That's the two big ones really opposite each other. The two medium-sized ones kind of opposite each other. And then this one's floating voter. And definitely not there. Not there. Just take this one out.
There you go, Elton.
Do you think just swapping these two round?
Try it.
No.
That's worse. How can it be worse?
We're learning nothing. Hold on, that's it.
Oh! This is the best we've got. And the only other possibility is if I just stand like this, then it straightens up. So if I just go to Elton and just like casually go, "Hi, Elton, here's your chandelier," then he'll never notice, will he?
It works for me.
I think that's a brilliant plan. Yeah. But actually, don't forget, because you're not working exactly. It's very easy when we're writing maths to presume that we're exactly this and exactly that. And you actually had to build the bucket, so you probably weren't working with
things were falling, torches were falling out.
Yes.
That was
water,
changing. The problem is, it was a dynamic problem, which is changing at every moment.
Yeah, absolutely. Well,
to your own
was
floristry
evaporating.
skills.
Yeah, a lot of things were changing.
It's exciting, actually, if you ask the students honestly to say how many of them got them. How many of you got? Yeah, see, less than normal in this, like whatever. It is a messy problem.
If you look at it in the right way, it becomes
problem,
less messy,
yeah.
I think. But, OK, well, I think you've got to commit and put your weights down, and then we'll see who actually got it to balance.
OK, Grant, if you go down that line here, but what balances mean, basically, if you draw a pair of X and Y axes, that there'll be no what's called a turning moment, a turning force that will tilt it one way or the other, right? And the turning force is given by the distance from there to there multiplied by the weight. So that, on that part, that distance and that will give a certain amount, 4.5 by whatever that distance is the same as 3 and 1.5 because it's the same distance.
Same distance.
So
it's that's easy that way.
Yeah, it's not going to flip that way, right? Then you go to this one, right?
Yep.
And you do the same kind of thing again, right? And that distance and that distance and that distance are the same, and this distance and this distance are the same. But if you add them up, that has, you know...
It's a little heavier over there.
A little heavier there, and it's a little heavier here.
So it's...
Yeah, now the actual distance are given by this very, very classic mathematical, you know, because the angles they're at, so they're halves and √3s over 2s. The key, by the way, is to get rid of the √3s over 2s. They're ugly.
Yeah.
Well,
really this one balances, so I think Elton will be happy. How about you guys? Where did you put your weights? Is it...
different to that one.
So, for example, if you did it down your y-axis, it would balance. It was exactly...
That's fine, actually. Yeah, that also works.
Yeah, exactly.
That works.
Well, I can confirm that you have both found different but correct solutions.
Nice.
That is a true draw for Braun and Brian.
I'm actually happy. This isn't false happy. This isn't where is my victory for math.
No, so I think there are multiple solutions to this, and basically you found the two good solutions. So I think Elton will be very happy. In fact, we could. Why not have two?
Well, that's fantastic. Come around and tell Elton you'll do it again. You'll just pop different, and also you can keep rotating. Elton won't know about symmetries.
It's always best to begin by simplifying the problem. So instead of the chandelier pivoting around a central point, start by imagining that the chandelier can only tip by rocking left and right along a y-axis or forwards and backwards along an x-axis. Now, force is measured in newtons. So a 1.5 kilogram weight here on hook 12 or 6 will not tip the chandelier along the y-axis, but will exert its full force of 15 newtons on the x-axis. And the opposite is true for weights on hooks 3 or 9. We've used a bit of trigonometry to work out the xy force on hook 1, and because all distances are equal, this will also be the yx force on hook 2. Once you've worked out all the forces in the x and the y directions for each of the baskets, there are a variety of positions we can place the flowers that will make the chandelier balance.
So overall, I think call it a draw.
I'm calling it a draw.
Perfect balance. This was all about balance.
Beautiful.
And I think
That's wonderful.
there you go.
How happy is that?
Yeah.
And the only dead weight. Right, no, I know. You'll have your victories. Yes, at the end of all that, on a happy, basically conciliatory tone that we don't normally have in the show, we want to thank everyone who's been involved. Thanks to our Gilded Youths, our students on our maths panel. Thank you very, very much, as ever. Thanks to our question setter and oracle of Oxford, Professor Marcus du Sautoy. But mainly thanks to our guest comedians who now can speak fluent maths and will never fall over again, for they will always move in a symmetrical balance wherever they go. And hey, thanks to Elton John for all of his help. Mainly to Richard Herring, Susan Calman, thank you very, very much. More of these problems guaranteed to get you thinking. Another time in School of Hard Sums. Thank you very much.
And now for your homework. 4 people who walk at different speeds must cross a bridge at night. The fastest takes 1 minute to cross and the others take 2, 5 and 10 minutes. They must use a torch to cross safely, but it has only 17 minutes of battery left. A maximum of 2 people can cross at a time, walking together at the speed of the slowest person. All 4 start on the same side of the bridge. Can everyone get across the bridge before the battery in the torch dies? Don't forget, someone needs to take the torch back each time as well. If you'd like to check your answer, or just cheat, go to the website joindave.co.uk.